Gas particles are in constant motion, but they're not all going at the same speed. Some molecules move slowly, some move quickly, and a few move incredibly fast. Because of this, chemists use different ways to describe gas speed, like average speed and root mean squared speed, each telling us something slightly different about molecules in motion. But here's the key question: what happens when gas particles are allowed to escape through a tiny opening? It turns out that gas's speed depends strongly on its molar mass, and the idea leads us directly to Graham's law, which explains why lighter gases effuse and diffuse faster than heavier ones. In this video, we'll connect molecular speed, temperature, mass, then use that connection to predict and compare the rates at which different gases move. At the same temperature, all gases have the same kinetic energy, but not velocity. Smaller molecules must move faster, and large molecules must be slower to maintain the same kinetic energy. In textbooks, they give you several ways of expressing the velocity of gas molecules. Let's go through some of those. The most probable speed, most of the times the textbooks will call this most probable speed. I think they do this in error because they call it mean. And this is not quite true. This is the most probable. And the formula is the square root of 2RT over M. Okay, this is the speed at the peak of the graphical distribution of velocities, where the actual average or mean velocity is the square root of 8RT over pi m. The RMS, or root mean squared speed, is the speed tied directly to the kinetic energy of the molecules. And we'll use the formula 3RT over m to represent that one. I'm showing you a distribution of the number of molecules versus speed. I have several molecules that are traveling much slower, which would be these molecules on this side. Okay. I have molecules that are going much faster over here on this side. Notice that it is skewed to the right because the fast ones are going much faster than the slower ones. Let's talk about how we would describe these. All right, so suppose that I had 5 people which is running around an oval track. Suppose one's going at 2 meters per second, one's going at 3, 4, 6, and 10 meters per second, respectively. I want to be able to describe their motions. So if I'm describing every runner, then I need to do what I would call an average, or the mean. That would be equal to 2 plus 3 plus 4 plus 6 plus 10. I'm going to divide that by 5 since there's 5 of them. That would give me 5 meters per second. So if I'm describing all the runners, then that's the way I would do it. If I want the faster runners to have a greater influence over my calculation, then I would use the root mean squared. So that's going to equal 2 squared plus 3 squared plus 4 squared plus 6 squared plus 10 squared. That would give me approximately 5.7 meters per second. So your RMS velocity will always be greater than your average velocity. The one that the textbook calls the mean, which is the most probable, would include this region here. This is the most probable. So it would be UMP. This will be URMS. Has a greater influence because it's showing the faster ones, because kinetic energy is more affected by objects which are moving faster. And if I include everything, then it's the U average. Graham's law for effusion and diffusion states that the rate of effusion and diffusion is equal to 1 divided by the square root of the molar mass. If I want to compare the rate of effusion of two separate gases, then I could say the rate of effusion of gas A is to the rate of effusion of gas B is equal to the square root of the molar mass of gas B divided by the molar mass of gas A. This is known as Graham's law. So you always know that the smaller the gas, the faster it effuses. So I like to put my fastest gas up here on the top, which is the one with the lowest molecular mass. And I put my slower one on the bottom. You don't have to do this. It just makes it easier doing the math later on. And it helps to avoid common mistakes at times. So calculate the root mean square velocity for the atoms in a sample of helium gas at 25 degrees Celsius. That's going to equal the square root of 3RT over M. Now, there's a couple things you must remember. This R here, we have two R's in the ideal gas law. Okay, here we have to use the 8.314 R because we're working in joules. And since we're doing joules and velocity, this has to be in kilograms here. The temperature must be in Kelvin as always. So to work this problem, I can say that the RMS velocity is equal to the square root of 3 times 8.314 times the temperature, which is 25. 25 plus 273 is 298. And all of this is divided by the molar mass of helium. If I look up helium on the periodic table, it says 4. That's 4 grams per mole. So I have to move the decimal 2 places to the left. That's going to make it 0.004. I plug this into my calculator, and I will get 1,363 meters per second for my velocity. And this is the root mean square velocity. An unknown gas has a root mean velocity of 481.95 meters per second at 298 Kelvin. So what's the molar mass of this gas? So writing my equation. And I'm going to be looking for the molar mass. So let's square both sides. Okay, I'm going to cross multiply and simplify it. So I get the molar mass is equal to 3RT over the URMS squared. So plugging in, we get 3 times 8.314 times 298 divided by 481.95 squared. All right, so I do the math. I get 0.032 kilograms, or 32 grams per mole. Compute the relative rate of effusion of argon to helium through a porous disk. So I'm going to say the rate of gas A over the rate of gas B is equal to the square root of the molar mass of B over the molar mass of A. I always like to put my fastest one on top. Okay, so I know that helium is faster because it has a smaller molecular weight. So I'm going to let the rate of A be helium. So I'm going to say X is to 1, because I'm going to let the rate of the slow one be 1, so that helium will be a number larger than 1. All right, the molar mass of B, I look up argon, and I see the argon is 39.948. Helium is 4. So I get 3.16. That means that helium is 3.16 times faster than argon. Okay, a very similar problem. What is the ratio of the velocity of neon atoms to the velocity of krypton atoms? Both gases are at the same temperature. So I picked my smallest one, which is neon. So I'm going to let neon be on top. There's going to be the molar mass of krypton over the molar mass of neon. I'm going to let my slow one have a 1. I'm going to put an X there. So I look up krypton on the periodic table, and it's 83.798. Neon is 20.18. So I get 2.04. That means that neon is 2.04 times faster than krypton, as it effuses through a small opening. So what's the molecular weight of a gas which diffuses 1/10 as fast as hydrogen? Okay, hydrogen is going to be my fast one. Okay, let's put x, wherever it is. It would be the square root of x over the square root of 2. There's two ways of working this. I can let hydrogen be 1 and the bottom one be 0.1, or I can let the bottom one be 1 and the top one be 10. So I'm going to say the second one. So I'm going to say 10 because the rate of x is 1/10, or that hydrogen is 10 times faster. It's equal to the square root of x over the square root of 2. So I know that the square root of x is equal to 10 times the square root of 2. So the square root of x is equal to 14.142. Square both sides. So x is equal to 14.142 squared. So x is equal to 200. Okay, that would be 200 grams per mole. If 0.2 moles of oxygen can diffuse from an opening in a vessel in 70.9 seconds, how long would it take in seconds for 0.2 moles of hydrogen to effuse under the same conditions? So I'm going to say the rate of hydrogen is to the rate of oxygen the molar mass of O2 over the molar mass of H2. Okay, we're not specifically given rates this time. I'm giving moles and time. All right, so if I have, for hydrogen, 0.2 moles over X amount of time, and for the oxygen, I'm giving 0.2 moles over 70.9 seconds. Okay, so these 0.2 moles cancel. So I have a 1 and a 1. I'm going to use what is known as the extremes over means rules. If I have a compound fraction, if I multiply the top of the top times the bottom of the bottom, that would give me 70.9 over the inners multiplied together, which would be x times 1, which is x. That's going to equal the molar mass of oxygen, which is 32, over the molar mass of hydrogen, which is square root of 2. So essentially, if you're giving time, the rate is equal to the reciprocal of the time. So you don't have to go through all this as long as they have the same number of moles. All right, so now we simply cross multiply. So x times the square root of 32 is equal to 70.9 times the square root of 2. Taking the square root of 32 to the other side, divide both sides by the square root of 32. So x is going to equal 70.9 divided by square root of 16. So x is going to equal 17.73 seconds. This is the amount of time it will take for the hydrogen to diffuse through the same hole under the same conditions. A given volume of carbon monoxide required 67 seconds to diffuse from a pinhole in a vessel. Under the same condition, another gas requires 79.7 seconds for the same volume to diffuse. What's the molar mass of this gas? So we're going to say the rate of CO is to the rate of X as the square root of the molar mass of X over the square root of the molar mass of CO, which is 12 plus 16 is 28. Okay, so the rate of CO is the reciprocal of 67. The rate of X is the reciprocal of 1 over 79.7. So by doing the extremes over the means, I will get 79.7 over 67. This equals the square root of X over the square root of 28. Cross multiplying, I will get 67 square root of X is equal to 79.7 times the square root of 28. I'll divide both sides by 67. So I get the square root of X is equal to 6.2945. If I square both sides, that will give me 39.62 grams per mole. Let's summarize what we learned. Gas particles are always moving, but they move at a range of speeds. We can describe these speeds using quantities like average speed and RMS speed, with RMS being especially important because it relates directly to kinetic energy. At the same temperature, all gases have the same average kinetic energy, but lighter gases move faster to have that energy. That's why molecular speed depends on molar mass. Graham's law captures the relationship by showing the rate of effusion is inversely proportional to the square root of molar mass. Thank you for watching. Please hit the like button and subscribe. I'll see you back soon with another video. Thank you.